and I have total 10+ years experience in FPGA designs, and also have a 2+ years experience in embedded system domain. Currently, I'm working as a FPGA design engineer, and my profile is creating the design for RTL using VSTL or Verilog, and also CDC checking, synthesize and implementation, and also the hardware testings. Today, this one is a high-speed protocol which is used for the image processing or video transfer from your one domain to another domain, or one source to another source. So this is the MIPI CSI. So this MIPI is one means microprocessor interfacing process interface, that is the full forms, and CSI, that is the camera sensor interface. And another one also available, that is the DSI, that is the display sensor interface. So we are using the CSI 2.0, and this one means project which where we are taking this MIPI CSI 2.0 protocols for transforming your video or image from FPGA board to one embedded hardware. So we are using in here, that is the Intel Area 10 hardware, and one AI purpose board which is used the Google Coral board. So MIPI generally, this is the high speed protocols. So anyone asks me that why we not use this SPI, because SPI is also high speed. But the reason here, it's a new protocols, and the speed is more than 2 SPI. So MIPI, it consists of 5 lane. That is the means 5 in main content. That is lane, packet, payload, sleep mode, transmission, and the virtual channel. So lane, it's just confirm that the data lane, so how many data should be transferred at a time. So that is lane are 1 bit, sorry, 1 lane, 2 lane, and the 4 lane also available. So we are choosing in here, that is the 4 lane. And I'm writing the code in here, that is the VSDL due to and it's also possible, means proficient and proficient also with the Verilog, but there's a client demand to taking they want actually in VSDL. So MIPI, CSI, TX and RX, 2 things is available. So first I will explain the transmitter part. So generally in the transmitter, 5 layer is there. That is the first one, that is application. Second, that is application pixel to byte, that is the packaging formats. And third one, that is the low level protocols and some LAN management. And after that, this PHY layer. So that's 5 process, means total 5 steps is there. So first I will take, that is the data formats. So application, that means your camera, one camera is connected, means camera is taking some image, and this image format is an pixel. But when FPGA or any FPGA receive the data, so FPGA didn't understand this pixel format, so we need to convert into either byte, or maybe you can choose the decimals also. So that's why one things, that is a pixel to byte conversions is here. And here we are choosing the 4 lane. So we each lane are 8-bit. So at a time we are taking that is the 32 bits data. And after that, that is the low level protocol. So in this low level protocol, we are means adding some rules, and I will explain these things. It's also the lane management layer. And finally, we are moving to the PHI, means the physical. So I want to share one, means explain one thing. I'm sharing one media, means one video which I already took it, means already captured. So this one is my system, and I want to this one is visible for everyone. Hello.
Yes, sir. Your folder is visible, sir.
Only folder.
Yes, sir. Video is not playing, sir.
Video is not playing. Now it's
video is visible. Yes.
Okay. So I'm taking a help the MATLAB Simulink. So actually, when you make the actual or any FPGA code, then you can't take a real-time image, right? So that's why I'm taking the help of MATLAB. So here you can use the image or any kind of things or video. This advantage is also available in the MATLAB, and this is for the actually simulation testing. Means your which code you make it, that code is performing well or not. So here you can see one clock data in WR and address. This one is my code. Here I mean this is one black box. So this option, when you click on it, then they want that which code you want to insert. So you can choose it and select it. So your code is inserted here. And this IN and this input, that is the 1 and 2, because 1 and address I'm giving, that is the 12. That is the one, means the global value. 1 I am giving, that is only read or write. So if you giving the value read, that means 0. And if you are giving the value 1, that means you need to write the value. So I'm taking the image, and this image is converted. You can see I am making one RAM. So here, when I display this, when I starting this video, then you can see there's a value. Now it's 0. After that, this value should be changes. Changes means when the data, I'm getting the data from the pixel, means the image, and this image data converted into this binary or decimal. So here, that is the decimal value I'm taking. So I'm just playing this video again. So you can see the data is globally changes. Two zero one 222. So this is the value 233 231, and this value is changes. This is your memory, means one RAM you create it. Pixel format is the 3D dimension, so it's not possible to take it. So you need to change into the 2D, and there's this 2D value stored into one matrix. Matrix means your one memory. So this one is your code. It's data in CLK. This is your black box, and you take it and you just real-time testing is done by the MATLAB. So you can see that the value is changes. So now I'm just moving to so application, that means you are taking the data means one pixel capture it, and also some control signal is there. Control signal, that means the left shift, right shift, and the when stop, and sometimes that type of signal. And now this is the second step, that is a pixel to byte conversions. And the next step, that is the low level protocol. So I'm just explaining low level protocol. So right now you can see that is a step one. So this is your image, suppose one RGB image, and this image pixel is just in this format. Means is if you take this value in the Excel sheet, then you can see that is the value. So you can choose as a binary, you can choose as a decimal. So for binary, you can get only the 0 and 1. 0, that means the black, and 1 means that is the white. So that is the black and white, and that is the RGB. So RGB has one concept, that 0 to 127, 0 to 127 one range. After that G, that is 127 to 179, that format. And after that, that is the black, 179 to 255, because our range is 0 to 256, to be over 8. Next, so that is the format, that is the pixel format into the binary byte format, so 8-bit decimal. And next I check into this thing into the model sims, and this data you can see first, that is the pixel to pixel frame to pixel 1 format. And this data, that is the pixel to binary format, this data is stored on RAM, and this RAM is I took as a 1 means around stored 2 to the power 24 or 31. That is totally depends on you, because you just change the value in the program. So as per your value requirement, you can change it. Next, that is the, now it's coming some protocol layer, because now the data part is completed. Protocol layer, that is the protocol layer is some layer that is enable the multiple data streams using one single interface, because you are sending the data to some host, data to your some point. So you have one host, and that is host, but that's the master, and you are sending the data to some slave. So that's the concept. So protocol layer is how means the multiple data streams may be tagged, and that's related to the data streams can be properly reconstructed. So I'm just explaining to you the second thing, that is one thing, one step is there, that is the low level protocol. So this one is the two things, SOT, start of transmission, is starting with 0, and end of transmission, that is 1. So its concept is similar, that is some not concept, that is start and EOT, SOT and EOT, that is the same as the same as with your I2C protocol. So quite means this one, but the next of thing is totally different. So after that, the lane management. So here total 1, 2, and 4, 3 type lane is available. So we are choosing that is the 4 lane communications. You can choose also 1, and you can choose also 2, 4. Here 2, 3 things we need to edit, that is the header, one thing, second one, that is a checksum, and one is the error correction code. So when I'm sending the data, that the data is correctly, means when it's received, the same data is received or not. So it has any warning. So I'm just checking checksum, and it has any warning, means the data is changes, then we are taking some error correction code, ECC. And also here used one header, that is the 8-bit header I used, that is the identifier. So 2 to the power 8, that means the 256 total header is there. Now D5. So D5 is the actually the physical layer is for the CSI2 implementations and is composed in between the 1 or 4 unidirectional data lane. So and one clock lane. So when the physical layer is coming, so it's just one clock, and the 1 to 4 means one block. That is the PHI block, where the high speed one clock in plus and in minus, that's the high speed, and 1 to 4, that is the data lane, and the output is just like that. So I'm sharing this thing. So yeah, so you can see that is the lane management. So suppose you are giving, that is the byte, means how to distribute these things. That the byte 0 to up to 8 means, sorry, each byte are 8 bit. So I'm taking 8 bit at the first, means in that way 1 2 means the first one is a 0, after that 1 2 3, and again that is the 4. That is because this is a 4 lane. So after 4 5 6 7, again that is the 8 9 10 11. In that way we are taking, and that is the lane management. So that is the actually data lane management, that how means how to take this data. So that is the snapshot, means the idea that we are taking in that way, and we are making the programming for in that way. So this is original because we are getting this one actually is not available in the Google or anyone. We are taking this PDF from the MIPI Alliance. So MIPI Alliance one means the main website is there, who just provide this data if you are registered. So actually you didn't get this kind of a PDF or any information from open source. So this one is the multi-lane physical layer. So you can see that the minimum physical layer is this construct requirement for this CSI2. That is the 2 lanes. One is the data lane module, and second one is the clock lane module. So both are the unidirectional master and high speed transmitter, and the low power transmitter, and the CIL MFM functions. And unidirectional master, high speed transmission, the low power transmitter, and the CIL MFM. I will explain this the CIL functions. Now this 2 lane, that means we are taking only the two lane, means 2 lane, that means we are taking 0 and 1. If you are this 3 lane, then 1 only the byte 0 at time. Here we are taking 4 lane, that means byte 0 1 2 3, and after that again 4 5 6 7. So in that way it should become. So that is the 2 lane, 1 lane, and the 4 lane data management. Now you can see that the designed ones means just describe in that way. That is the means the lane single lane management, and this is the 4 lane management. So we are taking this 4 data at a time in the byte 0, and again the next 8 bit, that is the byte 1, and we are in that way we are taking this thing. And after that, that's 4 lane management, that byte 0 is coming the first, that is the serializations first lane, and after that the second one serialization. So 2 things, that is the in case of the transmitter we are serialize the data, and in case of the receiver we are deserialize the data. So that is the main concept. And next, that is this is the lane management actually. So first, that is the byte 0, and in the lane 2, that is byte 1, and lane 3, that is the byte 2. And if you are taking this lane 4, then byte 0 lane 1, then it's coming to again the 3. Why 3? Because 0 1 2 3, then again 7. So 7, after that 11. So in that way it should become, because each bit are the 4 lane. So 0, 1, 2, 3, and after that again the 3 is coming. So this one you can see that is the 4, 8. So it should be coming in that way. But if you are taking this is 4 lane, then 0, 1, 2, 3. If you are taking 1 lane, then first is the 0, the again 4. After that 8. And if you are taking the 3 to 2 lane, then 0, 1, up 1, 2, 3, then 4 and 5. In that way. So first is the lane, that is start of transmissions, and this is the end of transmission, and this is the data management. But in between them, we are taking some protocols. Means we are already mentioned that is the identifier one thing, and ECC once, and also the CDs, cyclic clock, means the your warning checking. So that things is also added in there, and the total all things is going to as a transmitting part. So now there is the low-level protocol. So low-level protocols is the byte-oriented and the packet-based protocol that support the transport and of arbitrary data using short and long packet formats. For simplicity, all the example we can see that it's the single lane configurations. First one, that is the transport of arbitrary data, that is payload independent 8-bit watt size and support up to 4 interval virtual channel. I'm showing that's where is the channel is applicable, means applied, and special packet for the frame start and the frame end and the line start and the line end informations, and the description for the type and the pixel depth is one important, and the format of the applications, and 16-bit checksum code for the error connections. So that is the low-level protocols. Low-level protocol, that means the LB. This is some rules which is actually marched with your data management. Otherwise, it should be, suppose you are sending the data and it's received or not, you didn't get any reply. So you didn't get any feedback from your receiving side that your data is received by the slave or by the receiver or not. So that type of information you need to know. And suppose you also sending one some data and someone also sending some data, so it should be the collisions should be happen. So that's why we are taking some identifier. So you know that your identifier which you mentioned in your means just like that you are open 2 tabs, that is one is the Google and another one is the LinkedIn. So sometimes it should be collision if you don't have any identifier. So that's why we are making taking some identifier. Otherwise your internet every time you need the identifier, because LinkedIn has one identifier and Google, when you open in the new tab in the Google, or you maybe the Facebook or maybe the Gmail, it's means the different identifier is there. Otherwise it should be the collision, means you will get where, suppose if you not added, then suppose you open the Facebook, that time you also one garbage value should be stored, and the garbage value maybe the LinkedIn or Gmail or anything should be open. So that's why we are taking this identifier. This one is actually the your serializations, means the data watts. It should be the total first thing, that is the start of transmissions. After that, this is your data ID, which I already said, that is the 8-bit, and watt count, that is the that how many watts, that is a 16-bit watt. The receive means when you send the data, so the receiver reads the next watt count data, that is their and also their value. So the receiver is not looking any synchronized sequence within the payload data, and the receiver using the watt count value to determine means your end of packet. So that is the main means. Suppose when you are sending the data, so watt count, that means the counting, and the receiver waiting for the next data, that it should be coming some next data or not. So that is the main thing, that is the watt count, and this is 16-bit, and the data ID, which is the identifier, this is the 8-bit. After that one is the ECC, error correction, means when you are sending the data and it's received the data, so both are same or not. So that thing is performed by this ECC. And after that if you have one thing that is a checksum, that is a warning. Suppose you are sending the data and the data is changes. So these changes you can easily calculate by the data. So here the having lot of process means 2-3 processes available, but I'm writing this code for using by the or helping by this Hamming. So that is the thing. And after that, this data 0, 1, 2. So this is a package. So data lane management. After that, 6-bit checking. So it's also this 16-bit checksum also check this thing that it has any error. One means error or not. If it has any error, then it should be going to the first is check this warning. So if we have the change the data, then is ECC should be the 1, means generally this is 0. If it is has any error, then it should be 1. So that is the main concept. Next thing, and after that, there is the end of transmission. So start of transmission is starting with the 0, and this one is the end of transmission. So your total bit you can calculate, that is the 32 bit, and this is the actually 32 bits data value. First one, this is 16 bit 48, this one 128, and this is 1 and 1. So this is the 32 bit. Okay, the next is the low level protocol. So 32 bits total header, and 16 bit, that is the footer. That is means the checksum and packet data, and 32 bits, that is the 8 and 16 and 8. Now the 32 bit packet header is contain 3 things. One is the data identifier, 16 bit word count, and that is the 8 bit error correction, which I already explained. Now that is the packet data. So packet data, that is the word count. You know the word count, that is the 16 bit, and data word or width, that is the 8 bit. So the length is this is the 16 into 8, that is the total length packet of data, and there are no restrictions the value of the data word. So you can change the value. If you change the word count, then the length of this packet data should be changed. But the data what, it should be the same. It's constant. It's not changed. You can change only the word count. So your word count is the main integer. So you can control this value, means the data packet data, using by this word count. So this is one calculations. And packet footer, that is the checksum. So checksum just detect that the when you are transmission, means transmit the data, that the means it has any error or not. So it's only the one element. So it's very simple. So you need to just I make some code and also test it. So and also add it. And this is the total means the clock representation, that is the footer start of transmission, and packet, that is the start of packet, and packet header, and one is the packet footer. You can see packet header and packet footer, and in between these things, that is the data ID. Frame should be start, after that the first packet of data, and after that the packet header and footer, this is the last. So in that way it should be transmit. And this is H, that's the vertical valid, horizontal valid, and the data valid. Means when you are sending the data, then 2 things is 2 dimensions. If you consider this is the 2D, then X and Y. So X is the vertical and Y is the vertical and X is the horizontal. So these two, one is the same, and the data. So in that area which data should be sent, and when it should be high, that thing is the graphing. Next. So this is the block IP. So in this IP is consist, you can see that is the 2 lanes, 2 output. This is a CSI transmitter. So if you are choosing that is a 4 lane, so data 1, data 1 to data 0 to data 4, and clock N, and clock positive and clock negative, means the phases we are taking, that is a phase. So in the means one is the 180 just shifted. So
So you are
otherwise,
representing slide number 3. It is slide number 3.
no, this is CSI 2.0 transmitter, slide number 3,
Okay, fine.
not slide number 3. And this camera is contain means the is connecting with the CSI transmitter, and this one is the transmitter diagram. So start, end, foot headers, foot spread, back footer header and footer frames means the packet header and the packet footer, those things, and the start of it. This is the total internal diagram. And based on these things, you just write the code. Means suppose you have, when you have making the code for the I2C, then the start of transmission, then read write arbitrary, it means the acknowledgement. After that, the 8-bit data and address 7 or 10 bits. After that, 8-bit data, and after that again the acknowledgement and again the end of transmission. So you can sending the data means that is a sending and receiving rules. So this is also same, means we are following the in that way. So here you can see that is the total transmit. I'm just working with this transmitting. So in this transmitter block, so total 8 point is there. First one is the conversion data, pixel to binary, then marching and creating the frequency, because here the clock we are taking, that is the 1.6 gigahertz, but the which hardware we are used, that is the Intel Area 10. It's supported up to 200 megahertz. So we are making for 200 to megahertz to gigahertz range frequency using by the PLL, or you can you can make your own code. So this one thing, and after that, this filter and packet header error connection, that is a Hamming code, and the parity generator TXI DCC generation TXI is also there, and the spacing and merging to 1 to 7 in means all the 1 to 7 point merging into the one packet. So this is the transmitter block, and yeah, so that is the whole things. And if we are means need the code, means this code is also available, and it's all means it's already tested and also verify in the hardware system. Thank you. If you have any questions, or if you need to know any information, or have any questions, you can ask me. I will try to solve it.
Anyone have any doubt, any query? So basically, where we use all these things like transmission and all this diagram.
Yeah, this one is used for actually the high camera means the image processing, especially for the display, means your display, and this is the camera sensor interfacing. So now in today, everyone use this is this IP CSI2 or TSI 2.0. CSI again another version is available, that is the 3.0 is also available. So this is the 2.0. So the new versions is also fast, just changing means the changing the frequency and some extra control signal is available in for the 3.0.
Okay, sir. Thank you, sir. Thank you. So can we stop the class?